Hi, welcome to this session. I'm Hyunkook Lee from the APL of the University of Huddersfield. This session is about listening test design, and I'm going to give a broad overview of different types of listening test methods and also discuss some of the important basic principles to consider to design and conduct a successful listening test. The first half of this session will discuss various aspects about grading tests, and in the second half, I will introduce basic concepts of psychophysical tests and provide some practical examples. So let's first talk about grading tests. The aim of a grading test is to evaluate perceived sound qualities of audio systems using a certain grading scale. From this kind of test, we can ultimately establish a relationship between perceived sound quality or attributes and associated physical parameters. And many ITUR or ITUT standard listening test methods are based on subjective grading. A grading test needs to be designed to allow for proper data analysis. So if the design is flawed, then it would not be possible to conduct a meaningful analysis and draw a valid conclusion from the study. So in order to design a valid test, it's important to clearly understand some basic concepts such as experimental variables and hypotheses, between subject design and within subject design. And also we need to think about what type of scale should be used for grading, and whether to use multiple stimulus comparison method or single stimulus absolute grading method. And also the type and number of subjects to be recruited for the listening test need to be carefully considered. So when designing any experiment, we firstly need to clearly define our independent variables and dependent variables. Independent variable is basically what you manipulate, and dependent variable is what you measure. For each independent variable, we usually have several conditions, and the basic question we ask in research is usually, is the main effect of independent variable significant on the dependent variable? And if so, which pairs of conditions have significant differences? So here's a simple example. Let's say we are interested to examine the effect of microphone spacing on perceived spaciousness. In this case, the microphone spacing is our independent variable and spaciousness is our dependent variable. And we test several conditions of microphone spacings, so 0, 0.5, and 1 and 1.5 meters, let's say. And the subject grades each condition either in an absolute or relative comparison manner, and we can firstly visually inspect the data using the average values or error bars. In case of normally distributed data, we use mean values and 95% confidence intervals. But if the data are not normally distributed, then median and box plots or notch edges should be plotted instead of means and 95% confidence interval. If at least one pair of conditions has non-overlapping confidence intervals, it generally means that the main effect of microphone spacing is statistically significant, but this should be verified by appropriate statistical analysis methods. So how do we determine statistical significance of the effect of independent variable? We need to understand the concept of null hypothesis first. Let's say we have a hypothesis to test. The AB microphone technique, spaced omni microphone technique, is significantly greater than XY constant technique in terms of perceived spaciousness. Let's say this is our original hypothesis we want to test. Then in statistical testing, we have to flip this hypothesis, and we call it the null hypothesis. That's what the statistical methods try to verify. So the opposite of the original statement is basically the spaced AB microphone technique is not significantly greater than XY constant technique in spaciousness. And we test whether this null hypothesis is true or not. And the result reversely tells us whether the initial hypothesis is true or not. So if the probability for the null hypothesis H0 to be true is lower than a certain percentage value, then H0 is rejected. Then we can reversely conclude that the chance that the original hypothesis is true is very high. The probability value P determines whether to accept H0 or not, and the most widely used cutoff p-value is 0.05, which is 5% significance level. But 1% is also used for more conservative statistical testing. Now, what kind of statistical methods we need to use really depend on the type of test design and also whether the data allow parametric analysis or not. It's not the scope of this session to go into too much details about statistical analysis, but just to give a brief overview, when your test design is between subject, we'll see what between subject and within subject means later on. But if the design is between subject, then the appropriate methods to use are ANOVA for the main effect testing and t-test for pairwise comparison test. But if it is for non-parametric analysis, then we need to use something like Kruskal-Wallis test and Mann-Whitney test. Now, if your design is within subject, then we need to use different types of methods. Instead of using ANOVA, we need to use repeated measure ANOVA for the main effect and t-test for pairwise comparisons. If the data were not normally distributed, then we should go with non-parametric analysis methods such as Friedman test and Wilcoxon test. If you'd like to see more details about statistical analysis methods, I recommend Andy Field's book called Discovering Statistics Using R. And also there is a version for SPSS software as well. So what are the between subject design and within subject design? Firstly, in between subject design, basically each group of subjects tests only one condition, and the results are compared between the groups. That's why we call it either between group or between subject design. A good example might be a drug test. Let's say one group of subjects is treated with paracetamol and another group is treated with ibuprofen to see which drug is more effective for relief from headache, for example. Then this design, between subject design, makes sense because you can't treat the same subject with both drugs, in which case you don't know which drug actually worked or whether it was both that worked collectively or not. The result would be influenced by in which order you treated the drug to the subject. So in this kind of case, you want to strictly separate the subject groups for testing the stimuli. Then we use between subject design. But as you can imagine, this kind of test requires a large number of subjects in total, as one group only tests one condition. So if you have 20 subjects in group A, in this case, then you need another 20 subjects in group B. Then you need 40 subjects instead of 20 subjects. But if you use within subject design, all subjects test all conditions repeatedly. And this is the most common type of test we do in audio research. The within subject design is obviously more efficient than between subject design when there are many conditions to test. And it would also cost less than between subject design if you have to pay the participants. But this kind of design has a potential risk for what we call anticipation error, which means the subject can recognize the pattern of the differences between the stimuli and grade them in the same way without carefully listening to them. This is especially true in multiple comparison test scenarios. That's why the orders of stimuli within a trial and also the orders of the trials within a test need to be randomized for each subject. And we can also use a mixed design where between subject effect is examined for a certain independent variable and within subject effect is tested for other independent variables. In this example here, we divide subjects into two groups. So group A test 4 microphone spacings on spaciousness with the visual information provided on the screen. And group B is provided with the same microphone conditions to test, but without the visual information on the screen. So in this example, basically we are examining the between subjective facts of visual information and the within subjective facts of microphone spacings. We use this mixed design here because if you test both visual and non-visual conditions using the same subject, the subject who did the test with the visual condition first may give a similar result in the non-visual condition because of a potential learning effect. But we keep the within subject design for testing the microphone conditions because there are many conditions to test and it may be more efficient to test all these conditions within subject. And we can randomize the order of the stimuli in this case. Now let's move on to the question of whether semantic scale or continuous scale should be used. Semantic scales are used in all of these popular ITU methods like Mushra, double-blind, triple stimulus, ACR or DCR. So we are familiar with these labels such as excellent, good, fair, poor, and bad used in the scales in Mushra test or ACR test. But is this kind of semantic scale always necessary? In which case do we need these semantic labels, or in which case do we not need those labels? So let's first take a look at some examples of ITU methods. The ITU-T P911 recommends this absolute categorical scale. In short, we call it ACR. It's a popular scale used for QoE experiments, quality of experience experiments. It uses a 5-point discrete categorical labels. So excellent, good, fair, poor, and bad. And typically it's used for a single stimulus rating. And the result is presented as mean opinion score, MOS, Moser score. Each of these 5 points is given specific label, like I already explained. And it's up to the subject how they interpret these labels. The same labels are used also for the Mushra test, which we will have a look at later. The ITU-T 911 also introduces this degradation categorical scale. It also uses 5 discrete points, but this is for measuring the degree of degradation. So the labels are imperceptible, perceptible, but not annoying, slightly annoying, annoying, and very annoying. Well, this scale is sometimes criticized because it mixes the perceptibility and the annoyance in a single test. And the same DCR scale is also used in the ITU-R 1116 triple stimulus with hidden reference test. And this test is recommended to be used for stimuli with small differences, small impairment. So such semantic scales are most useful if you're interested in the absolute magnitude of grading results, like excellent or poor. If you want to find out whether a certain stimulus is graded in the excellent category or poor category, we need semantic labels like these. So they are most suitable for testing absolute quality of global attributes like basic audio quality or quality of experience than for specific low-level auditory attributes. It's because semantic labels can be quite ambiguous for low-level attributes such as source width or envelopment. For example, describing differences in perceived width by saying much or slightly can be quite tricky because it is difficult to define how wide is defined to be much wide or fairly wide. But saying excellent or poor in grading overall sound quality is relatively easier because the subjects have internal references about what is excellent and what is fair or what is poor. And often there is an absolute reference like PCM wave in audio codec testing, for example. Also, semantic labels and semantic scales could be useful for maintaining consistency between trials in absolute single stimulus rating test, like ACR test. It is possible to compare results between different test sessions or different studies when you use the standardized semantic labels like excellent, good, fair, poor, and bad. These kind of labels can be used consistently across different type of tests working on, for example, quality of experience. Then the researchers can compare results from different studies because the results were obtained using the same semantic labels. Of course, in this case, we have to assume that the interpretation of the semantic meanings are similar between subject groups. But one of the problems with the semantic labels is that the scale is not ideal for parametric statistical testing. It's because the psychological distance between each adjacent label might not be consistent. For example, distance between excellent and good might be fairly small compared to the distance between fair and poor, and the difference between poor and bad could be quite small too. So this kind of ordinal or categorical scale is not suitable for parametric test theoretically. However, if there is a large number of subjects used and the sample size is big enough, data could still be normally distributed regardless of the scale type, and parametric testing tends to be accepted in this case. For example, most QoE experiments tend to use the ACR scale and present the result using means and 95% confidence interval, even if the scale is not purely interval. But then to validate this, the number of subjects would need to be more than 30 at least. That's what the central limit theorem suggests. So basically, the sample size bigger than 30 is assumed to be sufficient for to assume a normal distribution, although the basis for this assumption is not very clear. On the other hand, a continuous scale is a purely interval scale, which is more suitable for parametric data analysis. There are usually just two end labels at the top and bottom of the scales, just to indicate the directions, and there is no intermediate label used between them. It's a more useful method if the main goal is to examine the relative difference between conditions rather than absolute magnitude of each stimulus rating. But more experienced listeners are required for a good consistency between trials. And also, you might not be able to compare conditions from different trials of different experiments because there is no label, and it's quite difficult to keep the exact consistency between trials and between different experiments. A potential error that could occur with a continuous scale is a range error. It's because different subjects would likely grade the stimuli in different ranges, even if the grading order is the same as seen in this example. This could lead to a large error bars and the statistical power will be reduced, which means the real difference between different conditions may not be revealed in the statistical analysis. So to avoid this range error, the ITU RBS 1116 recommends the use of data normalization technique. According to the group and individual means and standard deviations using this equation, we can reduce this range error. So now let's discuss pros and cons of multiple stimulus comparison method and single stimulus absolute grading method. Multiple stimulus comparison test like Mushra is probably the most popular type of test conducted in audio engineering. And this kind of test typically allows the subject to switch between the stimulus freely and listen to them repeatedly. And it may be considered to be more time efficient than a single stimulus test. But it is not always the case if there are many stimuli to compare. And if there are too many stimuli in one trial, it can lead to inaccuracy and inconsistency in the data obtained. And it also can cause listener fatigue. This kind of test is most suitable if you're to measure relative differences between different systems in terms of specific low-level attributes, like effect of interval cross-correlation on source width and effect of microphone spacing on spaciousness. So if you are very specific about the attribute you want to measure, and if there are subtle differences and some big differences within the stimuli set, then a multiple comparison test can be useful because your main aim would be to look into the relative differences rather than the absolute magnitude of each stimulus. Mushra is a well-known method specified in ITU BS 1534. This method includes a reference and hidden reference somewhere in the stimuli set, and one or two low anchors, typically 3.5K and 7 kHz, low-pass filtered version of the reference signal in audio codec comparison test. The reference is the original quality audio always, and the stimuli are compared against the reference as well as against each other. And this kind of test has been designed for testing intermediate audio quality. For example, this is a standard method for testing MPEG audio codecs. So Mushra always uses a reference on the top of the scale at 100 point. But do we always need a reference in multiple comparison test? The answer is it depends on what kind of test it is. So if it is a fidelity test where the goal is to see how similar a degraded or impaired system is to its original version, like an MPEG audio codec test, low bit rate audio codec test, we always have this definite reference, which is a PCM wave version. Then the reference is definitely needed. And in this case, regardless of whether we prefer the impaired version or not, if there is any perceived difference, the stimulus should be graded lower than the reference. But if it is a preference or QoE test, then a reference may not be needed or should not be used in fact. For example, the objective quality of low bitrate MP3 should be lower than the original version in fidelity testing, but MP3 could be actually preferred to the wave version for whatever the reason is. In that case, all of the stimuli could be compared without a reference. So in QoE test, reference is not always needed. There was an interesting study by Scheffler et al. In 2017. They compared the spatial audio systems 22 channel loudspeaker format and 9-channel speaker format and 5-channel and 2-channel stereo. They did a multiple comparison test to evaluate all these systems in two different ways. So in one test, they included 22-channel as a reference. And in another test, they included 22-channel stimulus just as one of the stimuli within the multiple comparison test. So as you see in this, the result graphs, when 22-channel audio was used as a reference, then it was graded at near 100 point. And there was a big significant difference between 9-channel and 22 channels. But if 22 channel was included as one of the stimuli and there was no reference, then the difference between the 9-channel and 22 channels became much smaller. And we can observe another interesting thing in Scheffler's result, which seems to suggest another limitation of multiple comparison tests with semantic labels. Here, the 2-channel stereo stimulus is graded in the poor category between 40 and 20, regardless of whether the reference was used or not. But this result is maybe because 2-channel stereo was compared against 22-channel or 9-channel speaker format. But if the overall quality of two-channel stimulus was evaluated in an absolute sense, it may not be graded in that poor region because in real life we listen to two-channel stereo all the time and don't compare the experience against 9 channel or 22 channels. So if we like the quality of the two-channel stereo and enjoy it in an absolute sense, then the quality of experience would be graded high. So perhaps multiple comparison tests may be more valid for evaluating relative differences on a continuous scale rather than using semantic labels. And semantic labels may be more valid in a single stimulus absolute grading test for global attributes like quality of experience, overall listening experience, or even preference. Because then we can evaluate each stimulus in a more realistic way. So in a single stimulus absolute grading test, there is only one stimulus tested per trial, and the subject grades the quality in an absolute sense, typically on a semantic scale. And this is more like a real life scenario because we don't do simultaneous multiple comparison in real life usually. And this type of test is more suitable for judging overall quality in an absolute manner, like when we test consumer audio systems and we measure quality of audio, quality of experience. This kind of absolute single stimulus absolute grading method is often used. But a single stimulus test relies on the subject's internal reference for absolute judgment because there is nothing to compare against the stimulus to be tested. And there is a potential order effect in this case. The previous stimulus tested can influence the grading of the next stimulus. The subject might be more generous or more conservative for earlier samples in the earlier part of the test. And as the test goes on, the subject might become more critical. So repeating the same condition several times in a randomized order is always recommended. Then you can minimize this kind of order effect. And if you randomize the conditions across all subjects, then this error can also be reduced further. So now the final point to discuss in the first part of this talk is about how many subjects are enough. More is always better. Well, in general, the bigger the sample size, the higher chance that we can achieve a normal distribution and a higher statistical power. And as mentioned before, the central limit theorem assumes that the sample size bigger than 30 to be sufficient for assuming normal distribution of the data. But the answer for this question, how many is enough, really depends on the nature of the test. If you are investigating the effect of technical features on a very specific low-level attributes like listener envelopment or source width, then you'd probably need more experienced or trained listeners who are familiar with the definitions and know exactly what to listen for. In this case, a relatively lower number of subjects might be preferred than in recruiting a lot of inexperienced and naive listeners because the data can be noisy if your subjects don't know what to listen for and they give you some random responses, then the more data is, the more noise you might have. So in this case, in this kind of critical listening test scenario, around 12 to 20 listeners may be sufficient, and these numbers are usually accepted in academic studies. Of course, the more the better. If you have more critical listeners and trained listeners, the more the better. But once you increase the number to a certain point and you start having some consistent statistical patterns, grading patterns, then you may not need to increase the number any further if you have enough statistical power to verify your initial hypothesis. So Of course, if you want to increase the sample size, each condition could be tested repeatedly by the same subjects, of course, in a randomized order. And also remember, the data that you obtain should be tested in terms of normal distribution before you conduct any analysis. Because usually, if you have lower number of subjects, there is a higher chance that your data are not normally distributed, and you should use non-parametric statistical methods. But if you're doing a less controlled experiment for like grading general preference or quality of experience of consumer audio systems, a larger number of randomly selected subjects would be preferred to a small number of critical and experienced listeners. And different subject groups could be actually recruited separately according to, for example, gender, culture, or age. And they could be split into different groups to conduct a between subject effect experiment. Additionally, for psychophysical tests or something like localization test, that typically involve many repeated trials or and require highly critical listening skills, a relatively small number of subjects are used in listening tests. But it is difficult to generalize the results in this case. So the results need to be analyzed and reported per subject rather than pulling all of the data together and give a global averaged result for every subject. Because if the number of subjects is only 4 to 8 people, always these results may have quite a large inter-subject variability, and it's sometimes difficult to generalize the result. So if the main focus is to examine human ability to detect or discriminate between different stimuli, then it is acceptable to use this kind of small number of subjects. But the important thing is that the results need to be reported per subject before you average the result. But after you obtain the individual the results, then those results can be grouped together, and you can have group mean and the confidence intervals, if you like.